Good morning, everyone. Today we'll be discussing about a star search algorithm using optical pathfinding using heuristics. So let's dive in. So before we start about A star search algorithm, we first should know what is A star search algorithm. So it's an informed search algorithm used to find the shortest path between nodes in a graph, and it is one of the most widely used pathfinding algorithms in computer science and AI. Also, is widely used in game development technologies and game mechanics. So, A-star search combines the strength of two classic strategies, which is uniform cost search and greedy best first search. So, when we talk about uniform cost search, it tracks the actual cost from the start node, that is G of n, and greedy best first search, it estimates cost to the goal using heuristics, that is h of n. So when we try to represent this mathematically, we will come across the core idea of the A star search, which is f of n is equal to g of n plus h of n. So as I told you here, f of n is the total estimated cost of the cheapest solution through the node n, and A star always expands the node with the lowest f of n. And g of n, which is actually here uniform cost search, it's the actual cost incurred traveling from the start node to the node n along the current path. And h of n, as I told you, is a heuristic estimate. It actually relates to greedy path first search. It's the heuristic estimate of the cost from node n to the goal, and it must be admissible. That is, it never overestimates. Moving on, if we look at the graph representation, we can look at the edges from A. So basically, when we look at our graph, it's a start node is node A. Algorithm begins here, and it must reach a goal G, target destination. And in between the nodes, there's initial node and goal node. We'll come across the intermediate nodes such as B, C, D, E, F, and each node is connected with its weighted edges. So the graph used to trace A-star search execution contains 7 nodes with weighted edges representing the traversal costs. So now here it may not be understandable, but we will also do a code implication to understand how it to better understand the graph and all. So as I told you, it also uses h of in the heuristic values, which estimates the remaining cost from each node to the goal G. These values are pre-computed and must be admissible. That is, they must never overestimate the true cost. And one more thing that like I want to clarify is that an admissible heuristic guarantees that A star will always find the most optimal path. A heuristic of 0 at the goal G is required. So when we calculate the heuristic estimate of from initial node to goal node, the node G will always have a 0 h of n. This is because the nodes closer to the goal in terms of estimates like C, D, and E have lower heuristic values, guiding the algorithm efficiently. Moving on, as I told you that if we expand A, we have to evaluate B, which has f of value 2 plus 6 equal to 8, and C, if we evaluate, it has f equal to 4 plus 4 equal to 8. Similarly, like a D if we do. So whenever we first come across an algorithm for to search tree, which we have to implement A star search, we have to first start with the initial node or the root node. Like here we are at start A, an open list. So since we are starting from initial position, the g of n will obviously be 0, and so it's f equal to 0 plus 7, which is 7. And then we have to expand A. Likewise, we expand B, and similarly, all the nodes must be expanded. And similarly, we have to do and continue the process. So at each iteration, A star pops the node with lowest f of n. As I told you, lowest f of n is considered from the open list, and it expands its neighbors, updates costs. The process continues until the goal node reaches G. uh, or the open list is empty. So moving on, if we see the if we apply the A star search algorithm for this search tree, the path will basically E to B, B to D, and D to G. So path selected is here, of course, the shortest path through the graph, and total cost is like G of G is equal to 4 is the cumulative edge weight along the optimal path. So if we see, why not the node C is considered. So if we calculate and say, likewise, then we see that path via C yields a higher cost, or we should say higher total cost. And A star correctly discards it because based on the f of n comparison each step, it has yielding higher values. And of course, A star search only considers the lower f of n values. So if we want to see the code implication, we can go through by following ways. I'm running the code in Google Colab. So here we can see how the code is working. So as I told you, that this is the graph. So A, here's A, and if we see A to B, it has uh, like G of n1 from A to B. Then A to C has a cos as 4. Then if we calculate from B, B to D it's 2, B to E is 5. Likewise, C to F is 3, D to G is 1, and E to F is 2. And like similarly, if we see the graph, we can see all the values of G of n, which is the uniform estimated cost or uniform cost search. So moving on, here you also have the value of h of n, which is estimated cost to goal G, which is corresponds to greedy best first search. Here with thoughts like A is 7, B is 6, C is 4, and if we observe it nicely, we can again see that G is 0 because since its estimated cost to goal G, so for the final node which is G, it is 0. This is something that we can remember, or a point to be note here. And as we continue, here we come across the code for the A star search. And of course, we are uh, supplying the function with two parameters, that is start and goal. So I won't go that much deep in the code since the main the main motto or the main of the agenda of this video was to explain A star search. So if you see here, we are basically using the one of the simple, basically simple code to represent A star search. Here we can observe that we are using while open list. So if any nodes which is unvisited will be added to the open list, and we are also calculating the h of n, g of n. So whichever if the subsequent nodes are yielding higher f of n, that node will be discarded, or that node won't be visited further. And here you can see that if a node is goal, return b. If the node is equal to goal, then we have return b and we will stop the A star search. If not visited, then we will continue and continue seeing and adding the node which has lesser f of n value. So here you are also at the end of we are running the function with the initial node as A and goal node as G. And we are printing the value of the path which we are getting here, and of course total costs. So if we run this code, I've already run this code in the before, just for any errors are there. So no errors are there. If we run it, we will get this output. The shortest path which we use, if we use the start search algorithm, we will get the same ABDG which I showed in the slide before. And of course total cost is 4. So now if we talk about we have like explain what is A star search and how its code is implemented. we can go on with the real world applications of this code or of this algorithm. So so we continue and to, like I told you, real world applications, how this A star search is used in real world applications and programs. So real world applications, first of all, this A star search is widely used in pathfinding algorithms. So whichever uh, programs or applications which requires pathfinding mechanisms such as GPS systems or game AI, networking routing, robotics, it's all used widely in these fields. And if we see in detail about each, so we come across this GPS navigation, which I have shown in the here. So A star powers turn by turn routing in systems like Google Maps, Apple Maps, or any kind of navigation maps found on the internet, and it helps in finding the shortest or fastest routes in real time. So, and similarly, if we look over the robotics part, the robotics use the A stars to plan collision-free paths in warehouses, manufacturing floors, and exploration environments. Collision-free paths is basically like finding a path without any hindrance or without any disturbing the other robots or like that in warehouses, manufacturing floors, and exploration environments. And also it is used widely, popularly used in game AI. NPC movements in games relies on A-star search to navigate terrain, avoid obstacles, and chase or flee the player. And is also used in networking and internet protocols, such as network protocols use A-star to determine optimal packet routes, minimizing latency and congestion. So whenever and during the old times, we didn't there is some latency, even though the distance between the user or the server or the sender it's minimal. But since we didn't have any optimal network protocols or any algorithms, latency was usually high, and often it was compiled with congestion problems. So we are using some high-tech, high-yield algorithms as A-star search or other pathfinding algorithms to determine the optimal packet routes. So here we come to the end of this video, and where I hope you understand what is A-star search and how the code implemented is done and its real-world applications and such. So before I end, I want to say a few words is that A-star search is one of the most powerful and widely adopted search algorithms in computer science and AI. Just true because it's used in a variety of fields such as game development, robotics, navigation applications, and it's also its elegance lies in its cost awareness with intelligent estimation. So So, as a quick recap, we see that it uses two best first search and cost aware heuristic functions such as greedy best first search. So it combines best of two worlds. It's heuristic driven. An admissible heuristic ensures that the algorithm never overshoots the goal. And basically, there's a saying that heuristic functions never overestimates. This is very true here also, and of course it's industry proven. It is deployed and used in variety of fields and industries such as navigation, robotics, gaming, and networking at scale. So with this I come to the end of the video. Thank you.